session analysis of seismic hydroacoustic and infrasound monitoring. I have the honor to co-convene this session with Ronan Lebras, who has served the PTS for many years from many positions, both inside and outside the organization. And he's also, I think most of you know him, but for the newcomers, he's behind GA and one of the main developers, I think, yes, of GA, the associator which has been until now the main associator in the PTS, but also a software engineer, acting chief, and many other positions. And with that, we can begin. Ronan, would you like to introduce the first?
Yeah, thank you, Christos. So the first talk in the session is by Benjamin Post from the CA in France, and the title is The Multi-Channel Maximum Likelihood MCMC Method, Extension to Multi-Source Estimation and Evaluation.
Hi everyone, thanks to you all to be here, and I will present you my work on the extension to the multi-source estimation of the multi-channel maximum likelihood methods. So let's begin with a little introduction on the infrasound technology. So the infrasound monitoring system is designed to detect an explosion of 1 kiloton equivalent TNT everywhere at any time on the globe. Today, 90% of these systems is operational. We can highlight the new station I-16 in China that is certified. And all these stations will detect a wide range of natural and anthropogenic sources like volcanoes, storms, explosions. And that's why detecting explosions in all these different sources with low SNR can be really challenging. We need, of course, some developments for the signal processing. For example, we have the HEF detectors that is commonly used in numerous NDC. However, it's principally used in a single frequency band way, and because we have a large variety of signals covering a wide frequency band, we developed at CA the progressive multi-channel correlation in '95. It's a detector based on the correlation, and the main things of PMCC is that we have a time frequency domain, as you can see in this picture. So this picture is from the DTK GPMCC view. So if you want to know more about all the DTK tools, you can come visit the stand of DTK. And here you have the example of a fireball above Japan that was detected last August by I-30 Japan. And what we can see here is the time frequency domain. And you have for each pixel of color the parameters of the azimuth or the velocity. And here you can see in blue, for example, the detection of this fireball. And so PMCC is used operationally since the 2000s at the IDC and is distributed to all the different NDC partners. However, we have some feedbacks when we have unfavorable observation conditions like low signal-to-noise ratio or interfering sources. We have a loss of detection and errors on estimations. That's why we developed new methods, a new signal processing method, the multi-channel maximum likelihood, based mainly on the likelihood methods. So for the detection, we are based on the generalized likelihood ratio, the GLR, and this GLR has a p-value detection threshold. This is a key point because it's a statistic threshold, whereas for PMCC with the consistence, we have an experimental threshold based on the experience of the analysis. And then for the estimation, we will maximize the likelihood of the maximum likelihood estimator. So we have the theta v, the azimuth and the velocity, the signal power, and the noise power. And thanks to all this calculation, we are able to calculate and estimate the SNR of the signal of interest, but also the uncertainty of the estimations. For example, as you can see on the equation, we have some variables that will control the uncertainty. The M is the number of sensors, the SNR, the frequency bandwidth, and also the time. The time window, the time window length. Here we have some examples on a data set of the station I-37 in Norway. We have at the top the example of the Ugatunga eruption, and what we can see here is the same things and is PMCC. So we have the time frequency domain, and in color we have with the azimuth. And what we can detect with PMCC and MCML is the direct arrivals and also the antipodal arrivals from the opposite point of the Ugatunga point on the globe. And we are able to detect with more detection with PMCC the secondary waves interacting with the microbaromes at the station. And on a larger data set, at the bottom, we can see the difference of detection between PMCC and MCML from 2023 to 2025. And what we can see is that we have almost 3 times more detection with MCML than with PMCC. And we are able to also detect and reveal the seasonal variation of the stratospheric guides. We can see that when there is no downwind toward the station, we are able to detect the microbaromes with MCML, whereas it's not the case for PMCC. And we are also able to detect these microbaromes at around 300 degrees, but also around 25 degrees. So we are able to detect when there is a low SNR conditions and when we are interfering signal of interest. So just a quick conclusion on MCML. MCML outperforms PMCC under unfavorable recording conditions. So when there is SOE interferences or low SNR, when there is a high SNR, it's important to say that PMCC and MCML have similar results. MCML is now optimized for real-time processing and will be implemented in DTK tools in the same time frequency space also. However, these 2 detectors assumes an hypothesis, a single source hypothesis, and as we can see in the examples, it is not valid in reality because we have secondary arrivals from the Ugatunga, but also the microbaromes, so it doesn't hold. So we have to, we want to try to detect several sources at the same time and at the same frequency. Several multi-source algorithms exist today, for example, music or clean, but it's not implemented for real-time processing yet, and we want to have a real-time processing for the mission. So we want to develop and evaluate a multi-source estimators and compare it to the state of art. So to begin with the development on the MCML-based methods, just a quick reminder of the equation of the recording at a sensor. It's when you have multiple sources, it's simply a sum of different signals of interest plus an additive noise that we assume a wide Gaussian noise. One naive method is to use a 2D peak finder on a monosource likelihood. So it's a really naive approach. Another approach is to stay in a monosource hypothesis all the time by subtracting the signals and iterate each time we want another sources. And it can be done because each time we are estimating the azimuth and the velocity, we can then realign all the signals and then subtract it by a certain percentage, here 25%. And then iterate. And here you have an illustration on synthetic signals. We have the likelihood function in function of the azimuth and the velocity. We have three sources. You can see it because it's yellow. And the red dots indicates the maximum. And then by all the iteration, we are able to subtract the right signals and then to estimate further sources. Final development is on the frequency component. So we have as in time the spectral matrix model in function of the steering vector and the power of the noise and the power of the signals. We can generalize it to the multi-source, and then thanks to the Whittle likelihood as an estimator, we can iterate to find another azimuth and velocity sources. We implemented it rawly or with an approximation in order to reduce the computational cost.
The protocol. Sorry to interrupt. If you could conclude within 2 minutes so that we allow some time for questions, you think?
Yes, I'm almost finished.
Thank you.
We have some protocols about I will be quick. We have several sources, different frequency bands, different geometries and SNR. And for the results, we can say that the MLE with signal deflation has the lower fast estimation rate. We have a lower fast estimation rate with a higher number of sensors or with a higher frequency band. Here we can say that music struggles with poor number of sensors. And finally, just to conclude before the conclusion, we have an event of interest. So we have PMCC and MCML, and then with these new methods, we are able to detect all the sources, the microbaromes, the Atlantic microbaromes, the Indian microbaromes, behind the main meteor, the fragmentation of a meteor here, recorded at the I-90 infrasound station at Djibouti. So in conclusion, MCML outperforms PMCC, especially at low SNR and when there is multiple interfering signal of interest. But it's currently undergoing tests at the French NDC and will be implemented in the DTK tools soon, and in the 1 or 2 years, becoming the new operational detectors. This improvement leads to the development of multi-source estimators, and the MCML with iterative signal deflation offers a cost-effective solution. Now for the perspective, we want to try to optimize the percentage of signal of interest that we want to subtract, and then do more systematic evaluations on different events of reference. And finally, we need a more robust cross-processing methods in order to build the events. Thank you.
Thank you. So I see Ron has taken all the praise and disappeared, so I'll take over from here. We have time for one question, but it may be that one of the speakers is not here, so we may have more time for questions later. But we have time for a question now. If there is any question from the audience. Or maybe I can ask a question. Do you think that this method could be also generalized to maybe seismic arrays?
In MCML?
Yes.
Yeah, MCML is currently under test on infrasound data, but we also done some processing on seismic data, and we can say that on the several examples that we use, we are able, for example, to estimate the coda waves after the main seismic arrivals that we don't always have with PMCC, for example.
Thank you. Yes, please, go ahead.
Thank you for the good presentation. I'm wondering if you had a chance to compare MCML method with FK method. Thank you.
Okay. Yes, in fact, the FK methods is beamforming methods like MCML. So I think it would be quite similar, in fact, because it's mainly based on statistics and likelihood. But here, the main power of MCML is that it's implemented in the time-frequency domain as PMCC, not as the F detectors that is maybe in the single frequency band. So here, the main improvement is that we have this kind of pictures. We can make more observation, more statistics on the different pixels on different frequency bands. But I think the FK is almost used, often used in one single frequency band. So I think the results in one frequency band is equivalent. I didn't make the test, but I think it's maybe quite similar. We have to do the test, but we have to have the same time frequency space between PMCC and MCML. That's why we have this kind of result, and we didn't compare to the FK at that time.
Thank you very much. So we can now proceed to thank the speaker again. And we can move on to the second presentation by Arif Adi Nugroho. So I should have said this before. At 10 minutes, I will rudely interrupt you to tell you that you have another 2 minutes, and then we will have some more time for questions.
Okay, thank you.
Thank you.
Good afternoon, ladies and gentlemen. My name is Arif Adi Nugroho. I'm from BMKG, the Indonesian Agency for Meteorology, Climatology, and Geophysics. Today I will present our research titled Detection of Underground Nuclear Explosion Using Fast-Peaking Techniques in Seismic Analysis. To begin, let me give a short background. The Comprehensive Nuclear Test Ban Treaty Organization, or CTBTO, plays a crucial role in enforcing the global ban on nuclear testing. The international monitoring system uses four complementary technologies such as seismic, hydroacoustic, infrasound, and radionuclide detection. Among these methods, seismic monitoring is the most effective for detecting underground nuclear explosions. At the heart of seismic monitoring is fast peaking, determining the exact arrival time of P and S waves. This step is essential to locate the source and determine if it is natural earthquakes or possible nuclear test. Detecting underground nuclear explosions is not easy. Many challenges. The first, the seismic signal they produce look very similar to natural earthquakes, but generate compressional P waves and S waves. In tropical countries like Indonesia, high background noise from ocean waves, rainfall, and human activity often makes weak signals. This makes detection more difficult and increase the chance of missing small events. This is why we need robust and adaptive fast-peaking techniques. Our research focus on three objectives. First, to compare fast-peaking techniques is the classical STLTI methods and the modern deep learning-based PassNet. Second, to integrate amplitude and spectral analysis to better discriminate between earthquakes and explosions. And third, to apply these techniques of CG station, CTBTO monitoring site, and other West Java in Indonesia sites to evaluate their performance in a noisy real-world environment. Our workflow starts with data processing. We apply to filtering, normalization, and windowing to remove noise and prepare the signal. And then we perform path picking using both STLTI and PassNet. And finally, we compute over S ratio and spectra feature to support event classifications. Traditional method, STLTI stands for short-term average over long-term average. This method compares short-term moving average with a long-term one to detect sudden signal change. For example, the P wave onset. It is strength, simple, efficient, robust for a high SNR, but it is sensitive to weak signal that STLTI might miss. PassNet, on the other hand, is a deep learning model based on convolutional neural network. It was trained a large global seismic dataset, which makes it robust, generalizable. The advantages are clear. It provides automatic detection, robust to noise, sensitive to weak signal that STLTI make. And next, in addition to path picking, we also compute P over S ratio. Explosions typically have stronger P waves because energy radiates astrotropically, whereas earthquake produce stronger S waves due to fault slip. Thus, P over S greater than 1 suggests an explosion, while P over S less than 1 suggests in earthquake. We use seismic data from CTBTO station in CG and stations West Java, CBGI, TSJM, and CMGI. The sites are located in a technically active area with subduction zone and volcanoes. This makes them an excellent but challenging case study due to the tropical noise environment. Here you can see the STLTI result. Seismogram top, STLTI ratio di bottom. We detect P wave arrival with SNR at about 8.2 decibels. But in many cases, STLTI fails to detect weak signal, especially during noisy periods. And PassNet produce much clearer peaks with a higher SNR of 25 decibels. This means it can detect P waves more reliable. And comparative result, this slide compares STLTI and PassNet. STLTI often misses weak signals, while PassNet gives robust and consistent peaks. This is why PassNet is becoming an important tool for operational monitoring. Ini example result to Posa in Italy. PNS ratio greater than 1 explosion, PS ratio less than 1 tectonic earthquake. At CBGI and TSGM and CMGI station, we obtain a P over S ratio of 0.65, again below 1. This is consistent with natural earthquakes. In summary, PASNet clearly outperformed STA-LTA under noisy tropical conditions. P over S ratio and spectral analysis improve even classifications, making our framework more reliable for distinguishing earthquakes from explosions. The improved framework strengthens nuclear test monitoring capability and contributes to the CTBT verification regime. And to conclude, deep learning peaks improve SNR from 8.2 to 25 decibel. Combining past peaking with amplitude and spectral analysis gives a robust and reliable monitoring system. We would like to thank you, CTBTO and BMKG for their support and collaboration. Thank you very much for your attention.
Thank you, Arief. Are there any questions from the audience? If not, okay, there's one.
Thank you very much for that presentation. So it's not just about the phases themselves, but you are subjecting the event to other discriminations. Is that the case? Because I've seen you are using PS amplitude ratios, spectral ratios. So it's not just the peak, you are also subjecting to other discriminants. Is that the case? Thank you.
Okay, P over S ratio compute to P wave S wave to detect nuclear explosions.
Okay, thank you. Let's go to the next talk now. Oh, there's another question. Sorry.
Yeah.
Yeah.
Thank you
Okay.
for giving me the floor. When you think of P over S ratio, maybe S means LG. Do you think about the path effect? For example, if the seismic wave propagates through the oceanic crust, that reduces the energy of LG. So the P over LG ratio looks like that from explosion. So did you think of that kind of effect, the path effect, when you apply the discriminant of P over LG? Thank you.
Okay. Okay, PNS P over S is from a natural earthquake. PSN ratio to detect natural earthquake. PNS ratio.
Thanks very much. So thank you very much. Let's thank our presenter again. And we go on to the next presentation by Vincent Bremo, and his title is Capabilities of Fiber Optic Cables to Characterize Seismic and Explosion Events, Case Study in an Underground Laboratory.
Okay, good afternoon, everyone. So I'm going to present you, thank you for the introduction. So I'm going to present you the capabilities of fiber optics cables, also known as DAS, to characterize seismic and explosive events. So quickly the agenda. So first, I will show you the description of the DAS experiment. Then we'll see some coupling and events location, and at the end, other events like earthquakes and thunderstorms. So first, the design of the experiment. So it was located on the southwest of France, near the Alps. So it's in an underground laboratory. So before it was a nuclear launch, missile launch base, and now it's converted to a laboratory. So we deployed fiber optic cables in the galleries. So you see in yellow the 3 kilometers of fiber optic cable, mainly in horizontal galleries, and one is in vertical. And co-located to the fiber optic cable, we deployed some accelerometers all along the galleries. And we did some explosive events, the red stars in the galleries and the green stars at the surface of the mountain. So here you can see some picture about deployment. So you see some fiber cables laid down on the floor, and you see we made some sandbags to put some sandbags on the top of the cable, and sometimes the cable is also attached to the walls of the galleries. Here you see an example of an explosive event recorded on the DAS system. So here it's in strain rate, so it's a unit of the DAS data. So on the y-axis it's the time, and on the x it's the fiber distance. Here you have more than 10 kilometers, and each traces is spaced by 1.6 meters. So it means that there are more than 6,000 traces. So it's like the fibers represent more than 6,000 sensors. So you see several times the events because the fiber cables is doing back and forth in the galleries. So we pass many times in front of the source explosion. And you see that we tried different coupling conditions and also different type of fibers with different providers. Here is some results about coupling. So it's just a zoom on the some galleries, and you see on the left 3 different types of cables. So the green one, the multisense, is covered by sandbags, and the red and the black cables are cemented in the ground. And you see on the right some traces, and the ones that are cemented are very close, fits very well, but the one with sandbags, we see some difference in the high frequencies. So the first order is that there is no big difference between the couplings and the type of cables, but we can still see some difference in the high frequencies. Now I move on to the location part. So I will show you 3 methods to locate some events. So the first one is the back projection of DAS data. So on the right, you see some DAS data, and we use the P and the F phases to locate the events. And we applied some filters like high cut 30 Hertz, and also we computed the envelope of the signals. And if we look at 23 traces spread in all galleries, we have a good location. So the true location of the source is the black stars, and we see the reds are close to the black stars, the red part. And if we look only around the source location, with 14 traces locating close to the source, we have a very good location of the shot. And it's only 15 meters from the real location. For the other methods, I need to pick some P and S waves arrivals. So here it's 6,000 traces, so I have to do it automatically. So I use the PhaseNet and the PhaseNet DAS. So it's two machine learning models. So PhaseNet is trained on traces. So here it's good when the traces are energetic. But there are still some errors. And PhaseNet DAS is trained on images. So there is a coherence between the traces, so that helps the peaks to be more continuous and coherent. So that's why we see some difference between the two machine learning models. And after, when I picked these arrivals, I used here the non-in-lock method. So it's a Bayesian with a Bayesian location, and it managed to get the confidence ellipsoid estimation. So here, for example, we see for the Ch2, we have an ellipse very close to the Ch2. And in X and Y, the uncertainty is very small, but we still have a big uncertainty in Z. Also, I implemented another method with a grid search method. So here we computed a 3D grid, and we computed the travel times between the fiber optic cables and the 3D grid. And here you see in the color bar, it's the residuals between the travel times computed and the peak on the data. So here also we managed to get the good location of the shot. Even in the Z location, we have a good precision. Another event here, it's an event at the top of the mountain, so it's a bit further. The peaks the data is a bit less energetic, so the peaks are less good, but we still have some coherency, and we can locate the event in X and Y with good precision. And also in the Z, we managed to get that the event is at the top of the mountain. So you see here, close to the yellow part is close to the red dot. Now I'll move on to other detection. So here it's another experiment in a field, and we managed to record the Myanmar earthquake. So it's an experiment near Paris, and here we see the events on DAS data. We see that the amplitude of the signals depends of the azimuth of the event and the direction of the cable. So I colored some parts to see where the signal have a good amplitude. And also we see some phase shift between the different direction of the DAS cable. Another event we managed to see, it's a thunderstorm or lightnings. Here we have an afternoon where there were some thunderstorm, and on the right you see some events on the DAS data. Now we want to create some algorithm to locate these events only with the DAS data. So to conclude, the fiber optics, the DAS system is very encouraging to detect events. We have to take care about the coupling to be sure to have a good sensitivity. And we want to check the sensitivity to see what is the minimum magnitude that we can detect on DAS data. We managed to get a good location of explosive events with DAS data, and also we see other events like earthquakes and thunderstorms. Thank you.
Thank you very much. Are there any questions from the audience? I have one question. Would you say that the DAS behaves a little bit like an array, a seismic array, in that case?
The DAS is converted as a seismic array, yes, exactly. It can, on several kilometers, it depends on the length of the fiber cable, yes.
Thank you.
We have time for one more question, maybe? Or then we can thank again. Ah, is there a question? Yep. There's a question.
There is
Yes,
one
please.
question, yeah.
Mr. Park.
For the detection of the Myanmar big earthquakes, is there any automatic detection algorithm, or the analyst find out the signal? My question is that, is there any automatic detection for the earthquakes or signal detection?
For the moment, no, but we want to create an automatic detection. The data are very huge, so it's complicated to detect it in real time. But it's something that we want to do. For the moment, I just look at this time window to see this event.
Thank you.
Thank you. So, why not? Yes, please.
Yeah, thank you. My question is just about this Myanmar earthquake. You identified this one with the fiber optic cable. How about the other technology? Without the fiber optic cable, was it identifiable at 8,500 kilometers?
Sorry, you mean about other sensors that detected this?
Yeah,
event?
the detection was, this detection was possible by the fiber optic cable, you said?
Yes.
So without the fiber optic cable, was it possible at this distance?
Yes, yes. We in France we detected very well this event. So also with the other sensors we detected. Yes.
So how was the difference between these two?
The difference with the fiber optics is we have a big array, so it's like you can see it on several kilometers, and it's like one seismic array itself. So.
Yeah, thank you.
Yeah.
Thank you very much. Let's thank our speaker once again. And we can move on to the next presentation by Andreas Kohler from Northstar, assessing deep learning for seismic array processing pipelines. Andreas?
Yeah, thank you. So in this presentation, I will talk about how we can use machine learning or deep learning and integrate it into seismic array processing pipelines. And the motivation is really, well, it's well known that the seismic arrays are a critical part of the IMS. So actually most of the associated arrivals come from detection on seismic arrays. There's been a lot of development. We already heard about FaceNet, for example, on single station processing using machine learning in seismology, but application to seismic arrays has not been the focus so far. So this is an overview about, like a simplified overview about the seismic processing pipeline, which is operational at the IDC, but also many other national data centers. So you start with a phase detection, then phase classification and back azimuth measurements. You associate the arrivals, and finally locate them, and maybe also do some event classification in the end. So traditionally, you do this on arrays with beamforming. So you create beams in different directions for different velocities, run an STR-LTR trigger on them, and then these pre-detected arrivals are analyzed further by FK analysis, for example. And then you can measure the direction and the velocity, or the parent velocity, slowness, and then from that you can get the classification into P, S waves, or other phases. So how machine learning can come into this pipeline? Well, first of all, we already heard in the phase detection phase, of course. We can use methods like FaceNet, eco-transformer, and there are many more methods out there now. And what they all have in common is that they include these convolutional neural network layers. They're organized in a so-called encoder-decoder structure. So they take waveforms and three-component single-station waveforms as input and transfer them somehow into a detection time series for P and S waves. That's basically how they work without going into much detail. And then you can also use machine learning in the second step. So you can try to use pre-detected arrivals and use some input to do the classification and measure the back azimuth on the seismic arrays. And I will show how we can do that. Finally, the event classification is there's also a lot of studies about that you can use also convolutional neural network layers, connect them to some dense neural network layers, and do some classification tasks like, is it an explosion, is it an earthquake, for example. Well, in this talk, I will only focus on the first two steps. And more in particular, this is the methods we are using and investigating in the pipeline. We use our own version of FaceNet, which is trained on a regional data set and also like modified slightly, adding so-called transformer layers into this network without, again, not having time to go into the details. So this is a published study, actually, but originally only developed for single-station processing. But I will show in this talk how we can apply this on seismic arrays. And then we have a method we call ArrayNet, which takes basically time differences observed on an array for detected arrival and as input, and then is trained to estimate from that the back azimuth of the incoming arrival and which phase type we observe. It's basically a combined regression classification neural network. So first I will talk about the first step, the phase detection. Here we identified three different approaches how we can use these phase pickers on seismic arrays. The first one is straightforward. We call this the ensemble detection method, where we apply the phase picker on all array elements in parallel, independently, right? And then in the end, you get this detection time series for P and S waves as output and combine them somehow. And combining means basically stacking them. The second approach is to train the neural network picker directly on beams. So then you do the beams from three-component data or vertical component data, and then do the phase picking on the beams. And finally, the third approach, which we call the array detection approach, is basically where you feed the whole waveforms of all array elements into the network to do the detection. So what the first, or basically the array processing is done at different steps for these three approaches. For the first one, it's done as a post-processing. For the second one, the beam detection approach, it is done as a pre-processing to create the beams. And for the last one, the array processing is directly learned by the machine learning method. The first ones can be trained on multiple arrays at the same time. So you have one single model applied to different arrays, while the third one is only trained for specific arrays. So we need an array-specific model to do that. And also the first two ones are a bit slower because you have to apply the picker on different time windows from different array elements or different beams in parallel, while the third one is only applied on time window, on one single time window including all the array stations. So now the second method, ArrayNet. I will talk a bit about what is the motivation for this method. So the conventional approach is to assume a plane wave traveling over the array, and that the back azimuth is identical to the source direction. And then you can fit the plane wave or do some plane wave fitting, basically do FK analysis or use some other methods like PMCC. And then you use a fixed velocity threshold to decide if this is a P wave or an S wave, or more like teleseismic phases, regional phases, and so on. The limitations with this approach is that we know that there are inhomogeneities below the array, which affect plane wave assumption. Also, you have back azimuth deviations, systematic lack of waveform coherency, and also the velocity thresholds varies between the arrays. And there are, of course, methods to deal with this, like empirical slowness corrections. But what we suggest is to use a neural network approach to do that. So which takes as an input, basically, these phase differences observed between all the array stations. This is shown in this upper plot there. So these basically time differences or phase differences in the frequency domain. And these are used to train a neural network to classify the phase type and to estimate the back azimuth. And the advantage with this is that you don't need a plane wave assumption, actually. You just learn from observed labeled data. And that's also a bit faster than FK analysis because you don't have to do a grid search in the slowness space. So we train all this method with a regional data set of events in Scandinavia, Northern Europe, and the European Arctic. So regional events. We're not going to teleseismic distances yet. And we use the data using IMS arrays, the ARCIS, Spitz, and the Finnis array for that. So first, now I will go into some results for the phase detection step. And how I do that, I show these curves here, which are the so-called recall precision curves, which is a kind of metric to evaluate the performance of a phase picker. We want to have a high recall. That means we don't want to miss real arrivals. But at the same time, we also want to have a low false alarm rate, so a high precision. So to have a good performance, we want to have a point in the upper right corner, basically. And we compute these metrics for different detection thresholds, and that's why we get this curve. And what you see here is the performance curve for P and S waves for single-station machine learning phase picker. Yes, and this is done on the test data set, which was not used for training the models. In addition, we also want to test this in more operational settings on continuous data, because that's really how we see if the model performs well, not just on test data, which just includes events. So here we applied on 4 days of continuous data with hand-picked events in this case, only on the ARCIS array, but we also have results for the other array. And what you see here in addition, the black dots, this is the performance of the operational classic array processing on the ARCIS array at NORSA. So that's our baseline, basically. Now I will add these performance curves for these 3 different approaches I introduced, the ensemble detection approach, the beam detection approach using either only vertical component or 3 components, and using the whole array as input. And you see that, first of all, for the continuous data, these all outperform the S-wave detection, which is first a nice observation. And also some of them outperform the P-wave detection. And when you compare this, and all of them outperform the single station detection method, which is kind of expected when you use more stations than just a single station. On the test data, you also see an improvement, which is mainly visible for these beam detection approaches. So this is maybe a bit more intuitive example how this method works. This is just one event, an example, how these methods perform on this one. So you see very weak regional events observed on the ARCIS array. You see the individual array channels. Then you see the beams. And on the bottom, you see the detection time series for P and S waves using 2 of these models, just for like, to make it a bit simpler. The array detection and the single station method. And you see, quite nicely see that you can even pick up this small, very weak SN wave, which you would not see in a single station processing. Now, switching gears a bit, now I'm going to the second method, and also this will show some results, but only one slide, and then I'm already close to the conclusions. So how we present the results for this method is a so-called confusion matrix, basically where you see the predicted label for given arrival and the true label. In this case, you see it for P, S wave, and also a noise class. And we want to have blue colors in the middle on the diagonal to have good results. And we have that. And actually, we also compared this with the operational pipeline, with SK analysis, and we saw some improvements. It actually also improves for, if you look like more like in trying to classify PN with PG, SN with SG, so the regional phases. Also, this works quite well with this method. And most importantly, when you look at the backasymuth residual obtained from classic array processing using FK analysis and this new method ArrayNet, you see that we improve we have a lower spread, so the lower residuals, and also remove a bias in the azimuth, which comes from systematic derivations of the backasymuth with respect to the true source. So that's encouraging results, and we also have a paper introducing this method out. So this brings me to the conclusion. So we have started to develop machine learning methods and integrate them into the seismic array processing pipeline using phase pickers on arrays and also using the phase classification using machine learning. And now we are looking into how we can combine, or how we can evaluate the combined performance of both methods in the pipeline processing to come a bit closer to putting this actually in an operational, into operation. Yeah. So thank you very much.
Thanks very much, Andreas. Very impressive results. Are there any questions from the audience?
As you work with deep learning, do you see that you are blind for untypical signals, for coming from untypical backasymuth, for example?
Yeah, that's a good point. So for if we train, for example, the phase classification then we have unbalanced data set because we train on real data. But for this ArrayNet method, actually we can add or augment the training data set with kind of synthetic events to take this into account. In that way, like simulating events in particular directions. And I looked a bit into some events which are like events which we don't want to miss, which are maybe not so often occurring. Yes, but if there's an event in an area which is not active at all, yeah, we have to look a bit deeper into that, how it performs. But in general, I think it is quite generalized over different areas. So I think it works well to also pick up events which are not that common.
Okay, thank you.
Thank you very much. So have you applied this method to other seismic IMS array?
Yeah, so we applied it to others. Okay, so we applied it to Arkis, Finis, and Spitz, the phase picker. The phase classification ArrayNet, we also applied to 3 other IMS arrays. I think it was Makanchi array, Texa array, and Garus array, I think, yeah. I think there was one more. But yeah, we did a test on this. So we trained the model on these arrays using arrivals from the LEB. And also saw that basically that it works.
So you observe the same performances?
Yeah, similar performances. Okay. Yeah. I don't have the numbers right here, but yeah. Mm.
So you don't necessarily need some 3 components array, right? Makanchi, for example.
Yes, yeah, I didn't mention that actually. So ArrayNet, they only use vertical component.
Okay.
The phase picker can also use the 3 components, yeah. But the ArrayNet, the phase is based on vertical component data.
Thank you very much. Very impressive.
Thank you very much. Let's thank our speaker once again. And the next talk was going to be given by Brent Delbridge from Los Alamos National Lab. Brent is unable to be here, unfortunately, and we have a very brave person in with us who is going to present it for him. So, and her name is Charlotte Rowe.
Thank you. Awkward. So this is not exactly my area of expertise, what Brent has done, but I will do my best to not butcher what he's trying to present here. So this talk is presenting methods developed at LANL for using seismic data in monitoring situations for event type discrimination and yield determination. We're specifically going to focus on using uncalibrated data at regional distances. Is this a slide attached here? Yes, okay. Why do we need these new methods, and why are we focusing on regional distances? The widely used methods developed for teleseismic distances have trouble when applied to regional distances and regional phases, which are required to observe these smaller events. Why are smaller events measured at regional distances more difficult? First of all, much lower signal-to-noise ratio, as you can see in these beautiful seismograms. Then also they're more difficult because we have complex propagation paths and waveforms, less impulsive, more emergent, and complex wave trains, as you can see here. If you go from array-based propagation model to a finite element model, especially when you're addressing the higher frequencies, you can see that the propagation becomes much more complicated. So here's our motivating example, the 6 declared DPRK nuclear tests. We'll use these events as quote-unquote ground truth, so to speak, so we can demonstrate this new method. Okay. What is the method from 100 feet up? Well, we take seismic waveforms, we do ratios of narrowband envelopes, we invert for seismic source information using the physical models, primarily looking at Mueller-Murphy 1971. So how does this work? When you're using the CODA, if you use earthquakes that came from a similar source area going to the same receiver, you remove site and path effects. And what you're left after you finish this analysis is simply the ratios, spectral ratios of the CODAs. Okay, so a few details on the method. We first do a narrow bandpass and produce envelopes at each of these narrow bandpass frequencies. We estimate a signal-to-noise cutoff. We estimate the CODA window. We take point-wise ratios of 2 events located close to one another on the same sensor component, aligned on the phases. And then we calculate the median of the point-wise ratio values in CODA window. We loop over all the components and all the frequency bands. The median of all the components for each frequency bin is termed the network average for the CODA spectral ratio. And it's explained in detail in the paper that's cited at the bottom of the slide. So here we've got some results for P and S derived source ratios of all 6 declared nuclear tests. Each pair in column 1 uses the DPRK1 as the denominator. The bottom row has DPRK6 as the numerator, and so forth. Note that we do not have any orientation effects, radial, transverse, or vertical, or all the same. We will use the P ratios to derive the source parameters, those being yield and depth of burial. Here we have an example fit using only DPRK1 and 2 nearby earthquakes. The inversion is done using Markov chain Monte Carlo, which gives us robust uncertainties, the full posterior after the inversion. And we do this for all 6 of the tests, either using each of the events by themselves and a nearby earthquake. We don't really need to know the magnitude, we just need the waveform, or all together. Using uncalibrated data at regional distances, we get similar answers as we do using calibrated methods or global teleseismic, etc. Punchline is using one set of an earthquake and one set of explosion waveforms measured on the same components without any calibration, we can give yield and depth of burial measurements that rival calibrated and global measurements. If we also use the S ratios, we can do discrimination as well. This can be thought of as an uncalibrated way to do regional PS ratios. P ratios versus S ratios discriminate at high frequencies above 5 Hertz. The far right plot is a statistical model based on the observations shown in the middle panel that is calibrated in a sense since it requires previous observations to be able to convert to a formal probability. So in summary, we demonstrate source discrimination and characterization methods that work at regional distances and do not require any a priori calibration or ground truth measurements. And that brings me to the end of the presentation. I wouldn't ask me any questions if I were here. But I encourage you to email or call Brent, and I'm more than happy to give you his phone number and his email address.
Well, thank you very much, Charles, for stepping in. So, yeah, as Charles said, we'll skip the questions. And the next talk.
I think the guidance we have gotten is to wait until the time comes so that people who are going from one room to the other can maybe attend this last talk, so we can have questions about previous presentations, if you have any. And I have a question about the first presentation, maybe. Is Benjamin here? Yes. So my question is, you showed in a slide that the MCML method makes about 3 times more detections than the PMCC. So my question is, are these all real detections? Have you made some kind of assessment of whether these detections are actual events, or maybe they are some kind of noise, false detections?
No, it's real detections.
It's all.
Yeah.
Thank you. That was a short answer.
I have a question for Vincent Brémaud, if he's in the audience. So would your method be superior to current methods in case you have a concurrent earthquake with a nuclear test?
I think the DAS method can be used in different locations, or maybe when you can't have sensors, you can deploy fiber optics maybe in deep water, or maybe in areas where you can't deploy the easily sensors. So maybe you can have a better detection with fiber optics. And also you have a huge amount of data with this kind of technology, so it can help for the detection and for the location of events.
Thank you. And I have the same question for the first presenter, actually, for Benjamin Post. So if we use your method on Seismic, do you think you could have a better resolution between 2 concurrent events?
For the MCML in the monosource, we will have the dominant sources. That's why my work was on the multi-source MCML-based algorithm. It's because if we have, for example, microbaromes in infrasound and an explosion, we want to be able to detect the both events. And what we observe is that we have a limit of signal-to-noise ratio. If the signal-to-noise ratio is too far from the dominant sources, then we are not able to detect the secondary sources. But for example, if we have -5 dB, 0 dB for the dominant sources and -5 dB for the secondary sources, we are able to detect it. So we have a clear limit, but we have to work on to maybe to improve the estimator and then to fix the limits of detection and estimation for the new methods.
Thank you. Any questions from the audience for the previous presenters?
I think it was the third presentation using DAS. Would you let me know the frequency band range of DAS, especially for the low frequency range? Thank you.
The frequency range, it's very wide, so you have to use, it depends of the parameters of course you use, and you can go in very high frequencies, so several kilohertz, but you don't need it. And in the low frequencies, the sensitivity is not very good, but we managed to see, for example, the microseismic peak at very low frequencies. So it depends of the parameters that you use at the beginning. So it depends of the gauge length. If you use a big gauge length, you can get some good low frequencies.
Actually, I have a question for you. For Myanmar, what was the low frequency range that you could actually see, and how high a frequency did you see? Obviously, it's teleseismic, but I'm just curious what you were able to see above the noise.
Yeah, so the image, the picture that I presented for this Myanmar event was with 70 meters gauge length. So we averaged the strain of DAS data each 70 meters. I also tried, for example, only 10 meters, but it was noisier. So for this low frequency events, I used 70 meters gauge length. It was about the hertz, maybe less than 1 hertz, yes. It was between 0.01 and 1 hertz. Yeah.
Thank you, merci Vincent. And I think we can now move on to the last presentation. Linda Silva will present us the Azores Infrasound Network. Linda, the floor is yours.
Good afternoon, everyone. So, my name is Linda, and my talk is about statistical analysis and characterization of the main detection on the Azores Infrasound network. I will start by an introduction of the Azores Infrasound network, and then I will present some event analysis based on the multi-channel correlation for a near data. And moreover, I will present the RMS analysis. So, the Azores infrasound, the Azores is located on the Atlantic North. It is comprised 9 volcanic islands divided into 3 groups. With focus on the central group, we have with focus on the central group, we have the IMS IS-42 station with 8 absolute pressure sensors. In 2022, during a seismovolcanic crisis installed in São Jorge Island, we deployed a portable array with 4 differential sensors in collaboration with the University of Florence. Last year, also due to a seismovolcanic crisis in Terceira Island, that started in that island, we deployed another portable array, this with 6 differential pressures. To complement our network, we have plans to expand the infrasound network to Fayal Island and Santa Maria, and for more information about that, you can see the e-poster on section 3.1. So, for the main feature, IS-42 has a main array shaped as a pentagon with a triangular aperture subarray and a maximum aperture of 2 kilometers. SG1 has a central triangular design with a maximum aperture of 130 meters, and the sensors are 400 millivolts sensitivity. The third array has a diamond shape with 2 centered sensors and a maximum aperture of 140 meters. In Terceira Island, we have 5 sensors with 800 millivolts sensibility, Pascal sensibility, and 1 with 100. So we use the multi-channel correlation analysis in the time domain, and we apply the window left of 10 seconds with a shift of 1 second, and also a bandpass filter of 1 to 10 hertz. This was in order to obtain detections characterized in terms of amplitude, back azimuth, apparent velocity, residuals, and frequency. Here we can see long-term observation of data from IS-42 between June last year and July this year, displayed on DIVA software. We can see the seasonal variations, namely in the dominating frequencies like the microbarons and the surf frequencies. And we can also see the behavior that in summertime the detections are mostly between 0 and 180 degrees, and during the winter time is between 200 and 350 degrees. The data here was used to compare with the seasonal variabilities that we have in our portable arrays. So here we have the portable arrays, the detections. In the first plot we can see the pressure, in the second the back azimuth, and then the velocity. We can see that we have a lot of background noise, but besides that we can see that during the winters we have a lot of detections that are associated with storms and also with the seismal activity. In December we had an increase in both islands. And you can see all the recurrent noise backgrounds and the same trends that we saw before. Here we have a storm that passed in October 2024 in the Azores, later related with Kirk storm. We can see it arriving firstly at SG1 and a few hours later to Terceira array with less ref. And this storm was detected in terms of high frequency and high amplitude. As I said before, we also have two ongoing seismovolcanic crises occurring in the Azores, and relating the earthquakes that we have, were recorded more than 1,007 earthquakes that fulfill our detections threshold, namely the distance of a maximum distance to the array of 20 kilometers, a depth of 10 kilometers, and a magnitude above 1 local magnitude. So after we choose the selected earthquakes, we plotted the earthquakes and all of our detection in Terceira Island. We also did the threshold of the detections by applying a time delay and azimuth deviation of 10 degrees. In the second image, you can see the plot of all the earthquakes, and the blue dots that are not that visible, but correspond to the detections in our station that could be correlated with the earthquake. So our results show that 40 events were detected and are associated with shallow earthquakes with magnitude larger than 1.5 and distance less than 12 kilometers from the array. You can see in the first images the detected ones are the ones with a red circle. We applied the same method to São Jorge Island, and from the 122 events selected, 16 were detected, and the results are the same. We had shallow earthquakes with magnitude larger than 1.5 and distance less than 12 kilometers. Additionally, and to understand the variability of our portable arrays during the seasons, we applied the RMS for each one of them, and we can see in the first plot that for the SG1 we have a more constant RMS value that is increasing in the winter times. In Terceira Island, we have a lot more variation, namely during the daytime. If we correlate the two of them, we can see some pikes, namely in the 10 a.m. and 3 p.m. in autumn on Terceira Island. In summer, we have more or less the same pattern in the both arrays, despite the last pike at 9 a.m. p.m. In spring, we have, you can see, you have a lot more pikes in Terceira Island, and in winter we have the same values, but with a lot more variance. So we went to see the back azimuth of each pike in Terceira Island, and the detections are consistent to the west, and we have a query in operation during the daytime in the same back azimuth. So, in conclusion, for a one-year detection, we saw the expected seasonal variation in all the arrays. Regarding the storms, produced high energy detected in the arrays in terms of high amplitude, more than 0.5 Pascal, and high frequency, more than 2 Hertz. The earthquakes detections in the arrays depends on the hypocentral shallowness, the magnitude, and the distance to the array, and also the noise level at the array. We saw, and this is also a conclusion, that the Terceira array is affected by local source of energy during daytime, namely the query that we saw that is at less than 2 kilometers from the array. São Jorge is free of those occurrences.
Thank you very much, Linda. Any questions from the audience? So you presented results for earthquakes which were local earthquakes, right? So,
For local work, yeah.
do you also have maybe mining events on the islands, or some mining explosions, mining events?
Yes, we have, and this was just a few events that we detect, but we also have mines. We detect airplanes and bolides.
Okay.
We have other.
And for the mining events, is the threshold lower than for earthquakes, or is it comparable?
We have to study that.
Okay, thank you. Any other questions?
Yeah, for the earthquakes, were you able to determine Beckhardsmut and slowness? So I was just wondering if you see on the infrasound network the seismic wave, or you see an air pressure wave.
Okay, you are asking if my detection is about, it's related with the seismic wave or the...
Exactly,
wave?
yeah.
Yeah, so this is a preliminary study, and we already had an acoustic wave. So this is selecting the ones that can have the acoustic wave to further ongoing work. So.
Okay.
Yeah, my question is about PMCC processing for your other stations, the ones that are like with small aperture. Did you use the same PMCC processing than for I-42, or basically it's like what are the limits of the PMCC processing for the smaller stations when compared to I-42?
Our stations compared, so IS-42 also use the PMCC.
Mm-hmm.
Sorry.
Let me clarify it.
Yeah,
what kind of processing did you use for the smaller stations in terms of, for example, the frequencies that you selected or the frequency ranges that you use for obtaining the detections? Is there any difference with the I-42 processing, or is basically a shared configuration processing for all of those?
Yeah, it's basically that, yeah.
It's the same?
Yeah.
Okay, okay, cool.
Thank you for your questions. Let's thank the presenter once again. And, I want also to remind you about the poster session for this theme, 3.5, and I believe it will take place tomorrow. So check your schedule for tomorrow, and please attend as many posters as possible for tomorrow. And let's thank once again all the presenters, and especially Charlotte Rowe, who stepped in with less than an hour notice to present the work of her colleague. Thank you very much.